Hey guys, this is Andrew with HKN, and today I'm going to be talking more about the Fourier transform and the bandwidth of signals. So a bandwidth of a function is the width of the frequency spectrum in the frequency domain. So you take a signal f of t, varying in time, and you find the frequency components of it by taking the Fourier transform. And so in the frequency domain, it'll look something like this function here. And the function will go from negative b over 2 to positive b over 2 as a domain, where b is going to be your bandwidth. So it's just the full length from negative to positive. These will always be the same for real valued signals only. The Fourier transform of real valued signals, where the domain and range of the f of t are all real numbers. They'll go from the negative frequency to the positive frequency. You'll never have this side be longer than this side as long as your functions are real valued. So what we're going to do is we're going to find the bandwidths of these four functions that are all comprised of sinc functions. So in previous videos, I found the Fourier transform by doing the integral. Today we're going to do what most people do, which is just exploit the table that we have here. And I've picked out the three values that we're going to have to use. That is the Fourier transform of sinc of omega t, sinc squared of omega t, and the property that if you multiply two functions in the time domain, it is 1 over 2 pi times the convolution in the frequency domain. So let's look at the first one here. So our signal here is f of t equals sinc squared of 100 pi t. So the substitution we have to make to match this table is that omega 0 is 100 pi. So very easily we can just do the Fourier transform. We know that omega 0 is 100 pi. So pi over 100 pi is 1 over 100, or 0.01. And then we have the rectangle function. Sorry, not the rectangle function, but the triangle function, because I was pointing up here, but we're at sinc squared here. So we have the triangle function, which is defined down here as going from negative 1/2 to 1/2 with a height of 1. So it's an equilateral triangle centered at the y-axis. Of omega over 2 omega 0, so omega 0 again is 100 pi. So we get the triangle function of omega over 200 pi. So this is our Fourier transform f of omega for f of t and a here. So if you were to draw this is what this would look like. It would have a height of 0.01 at 0. And because it goes from negative 1/2 to 1/2, when you divide by 200 pi, it comes out to negative 100 pi and positive 100 pi. And you connect these points linearly. So if you look at the total width of this function in the frequency domain, so you just look at the domain from lowest part in the domain to the highest part in the domain, you find that the bandwidth is 200 pi radians, which is also equal to 100 hertz. So a system that you have that would be taking this signal as an input or output has to have a bandwidth of 100 hertz. So it has to be able to support all frequencies less than 100 hertz. So now we're going to move on to letter B here, where letter B is 0.001 sinc squared of 100 pi t. So when we're doing this, we want to find the Fourier transform of this guy, f of omega. We've already done this because sinc squared of 100 pi t is existent in both of these, and the only difference in B is that we're multiplying by some constant value. The Fourier transform is an integral, and we know that constants are pulled out of integrals. So all that multiplying a function by, when you take the Fourier transform of it does, when you multiply by a constant, all it does is multiply the Fourier transform by the same constant. So this f of omega is the same as this f of omega, just multiplied by an extra 0.01. So it would be 0.0001 of the triangle function of omega over 200 pi. And what you'll notice is that the constant out front here, so the multiplier out front, doesn't affect what frequencies this comes over. It affects the height and the magnitude of the frequency, but it doesn't affect which frequencies are there. That's all by the rectangle or the triangle function here, the triangle function. The rectangle for a regular sinc function. That's all determined by those, and also whatever your modifier on omega is. So our function is going to look very, very similar, just with a different height. So the bandwidth here is the same as in the previous, 200 pi radians, or 100 hertz. So multiplying by a constant does not affect bandwidth. All right, guys, so now we're going to move on to letter C here. So letter C here is we switch from sinc squared functions to a sum of a sinc and a sinc squared function. So the Fourier transform of a sinc function is pi over omega 0 rectangle of omega over omega 0. So as where the rectangle function is defined from -1 to 1, where it's 1 everywhere else it's 0. So it's a switch on, switch off at -1 and 1. So if we were to take the Fourier transform of a linear combination, it's a linear combination of the Fourier transforms due to the linearity property of the Fourier transform. So we end up with, if we take the Fourier transform of sinc squared of 100 pi t, we get pi over omega 0, so that would be 0.01 times the rectangle function of omega over 100 pi. And that's that first one. So now we need to take the Fourier transform of this guy here, 3 sinc squared of 60 pi t. So if we take 3, because the constant just comes out front, so we get plus 3, times pi over 60 pi. So that's 1 over 60, or 3 times 3 over 60. Sorry, 3 over 60. 3 over 60 is 1 over 20, or 0.05 for our modulus out front there. And then we get the triangle function of omega over 2 omega 0 here. We end up with 200 pi. Sorry, 120 pi. So we're adding these together, but we really don't care what this graph looks like. We just care what the highest frequencies are. So in the triangle function here, we go from positive 60 pi to negative 60 pi. So the bandwidth of this function is 120 pi. And the bandwidth of this function would be, because the rectangle is defined from 1 to 1, and we have 100 pi here, it goes 100 pi to 100 pi, so it's 200 pi. So the bandwidths here are different for each function, but because this one's bigger, we take the more stringent requirement, being that this needs to get all of this. It needs to get all of the function, and even though this function can be perfectly captured by something that is less than this, you need to capture all of it. So you need to capture all of the functions, so you need to have it be higher than 200 pi. This is radians, or if you want to put this into hertz, it's 100 hertz. So if you have a linear combination, you take the larger number to be the total bandwidth. So now we're going to move on to D here, and D is the multiplication of two sinc functions of different frequencies. So this is where we're going to imply that the multiplication of two things in the time domain gives you the convolution in the frequency domain times 1 over 2 pi. So we're going to ignore the moduluses now because I'm sure I hope I've convinced you at this point that these numbers out front don't end up mattering. So we just want to know how far out these functions go. We don't care what the magnitude of them is at that point. So what we're doing is if we take the Fourier transform of the first thing, so if we have f of t is the first one of omega being omega 0 equals 50 pi. If we take the Fourier transform there, what we end up is we get the rectangle function of omega over 50 pi times some constant. If we take omega 0 to equal to 100 pi, we get some constant times the rectangle of omega over 100 pi. So these two functions are going to go from positive 50 pi to negative 50 pi, and then positive 100 pi to negative 100 pi. So that means that the bandwidth here is 100 pi, and the bandwidth here is 200 pi. The bandwidth is also considered the length of your function. So if you were to sit at one point and watch the function go by, this would be how long it would be going through in the frequency domain. So when you convolve things, the length of the convolved function is the sum of the lengths of the original function. So what that means is that the bandwidth of the multiplication of the two functions, with bandwidth 1 being 100 pi and bandwidth 2 being 200 pi, the total bandwidth is just the sum of the two. So when you add two functions, the bandwidth is the higher one. When you multiply two functions, the bandwidth is the sum of the two. So if we do this, we get that the bandwidth is 300 pi radians, or equivalently 150 hertz. All right, so I hope you learned something about bandwidth here today. I'm just going to mention one thing. So if we have a system that needs to have this bandwidth, we also would like to know how fast we need to sample our functions, because say for instance that we are using a digital system instead of a analog system where we need to sample. Our sampling rate for our sampler has to be twice the bandwidth. So wherever our bandwidth value is, so for instance for this, if we're sending this signal through our system, we need to sample this signal because the bandwidth is 100 hertz. We need to sample this signal at 200 hertz. So that's 200 times a second. Similarly down here, because for this function, our bandwidth is 150 hertz, we need to sample our function at 300 hertz, or we need to take 300 samples every second. So that's called the Nyquist Criterion, and all it simply is that your Nyquist frequency, call that NF, is equal to 2 times your bandwidth. And this is for all functions. So I hope you learned something today, and have a good day, guys.